So today we're going to begin our graph theory review, and looking at the calendar, we don't have many weeks left until the CCC date, which I think is not sure, like around the 17th, I believe. So at most we have like 6-7 weeks, and yeah. So today we're gonna begin our graph theory review. We're gonna talk about BFS, DFS, Dijkstra's, and Kraskel's algorithm, and that's for minimum spanning trees. I think those of you coming from the junior stream, you might already be familiar with BFS and DFS, and maybe even Dijkstra's algorithm. But the purpose of today's class is to make sure you know how to implement these algorithms in C++, and just for you to review these algorithms again. And so let's first talk about BFS. So BFS is an algorithm that traverses the graph by going down the levels one by one. And so the common applications of BFS are reachability. So for example, like, can this node reach another node in the graph? You can use it for cycle detection. If you visit another already visited node in the graph, then you know you have a cycle. You can use it for a single source shortest path in unweighted graphs. So if you have a graph with all the edges, where all the edges are of length 1, then you can use it for to find the shortest paths, because of how it works. And so I actually have a graph to demonstrate. So if I perform a BFS on this, that's not what I wanted to do. Okay. If I perform BFS on this from the node 1, it's first going to go to 3, and then either to 4 or to 5. Say it goes to 4, and then we're going to perform our BFS to 5. And so gradually it'll go to 7, and then from 5 it'll go to 6, and etc. So as opposed to depth first, it's going breadth first. So it's going to go as wide as possible, just going down each level, and using that property, we can use BFS to find shortest paths. And we're actually just going to implement that right now. And so using BFS, I have some example problems here, but I thought it would be easier if I just took this graph and just implemented the shortest path BFS on this graph. And so I'll paste in the input from here. So let's have the first two integers, n and m, be the number of nodes and the number of edges. And following that, we have the edges. And so, okay, let's take in the number of nodes and the number of edges, and then let's take in all the edges from the inputs. So in this case, we have a directed graph. I'm going to assume you guys know what the terms are, so what a node is, what an edge is, what directed and undirected mean. And directed just means each edge only goes one way, so this edge is directed from 4 to 7. And an undirected graph would just mean you can use this edge to go from 4 to 7 or 7 to 4, and so on. Okay, so if we have a directed graph, then all we do is we put in, we usually, when we implement BFS and competitive programming, we're using adjacency lists. And how we declare an adjacency list in C++ is we would just put a vector int as the thing that each array element is storing. And then we're going to put a name for the variable, so for example ADJ, and we're going to put the number of nodes we have here, and so the maximum number of nodes, let's just say 10 in this case. So let's just make a graph with an adjacency list of length 10, and so in here we're going to put adjacency at A. This would store all the nodes that are adjacent to A. And so we put ADJ at A dot either in place back B, This would work. You could also do, let's say, push back. That would work as well. So that what that does is it adds B into ADJ of A. Okay, and so for a directed graph, this is all you have to do. For an undirected graph, the only difference is you would just put this, except now you make A and a neighbor of B as well. And so you just do adjacency of B dot pushback A. And so that would make it undirected, but our graph is directed in this case. Okay, so now that we have our input, we can start our BFS. So let's make an array called distance, and I'll also make that of length 10, just because our graph is small. In an actual problem, you'll make this whatever like the maximum number of nodes is. So you say like n, or like the constraints on n. Okay, so with our distance array, what we're going to do first is to fill it to infinity. So fill the array such that each element is represented by infinity. But the problem is, in programming languages, there is no concept such as infinity, because your element can only store a finite value, right? So instead what we do is we just put a very large number there so that it won't ever reach that number. And so compared with every other number, it's going to be the largest integer, which kind of acts like infinity. Actually, I can put some comments here. So, okay, and a common thing we do here is we use the Memsat function. And so that takes in the name of the array you want to fill, and the byte you want to fill it with, and size of as the last argument here, just to tell it how much it needs to fill it up to. And we're gonna fill the entire array with a very large integer. And so if I actually print out what's inside of the distance array here, so if I go I equals 0, I is smaller than 10, plus plus I, and if I output this array like that, oh, what did I do? Oh, okay. I didn't declare my variables. You're going to see that they're filled with just in general a very large integer, and so for the purposes of this problem, it's enough. In case you need longs, this trick will still work, because it's just going to fill it with another very, very large integer, because we're using the size of function here to fill it up. Okay, so getting rid of this. This is filling each in the array with large integers. Okay, and so the distance array is going to stores the distance from node 1 to node I. So, okay. And so for node 1, we know that the distance from node 1 to node 1 is going to be 0, so we can directly say dist at 1 is equal to 0. And remember that we need to use a queue to implement BFS. And in Python, you would be importing a queue. In C++, if you have this header here, you can just say queue and then your data type. In this case, we're using integer for node, and so let's just call that queue. And we can say queue.push 1. And so that's going to push node 1 into the queue. Okay, and so now we can start our iteration. So while the queue is not empty, so we can say that by saying while not queue.empty. And so that's if queue is empty, then this is going to return true, and this is going to negate it, so it'll be false. Then what we can do here is first let's declare node just to pop out the current front of the queue. So how we retrieve a node from the front of the queue is we use queue.front, and how we pop out a node from the queue is we use queue.pop. Okay, so Now we're gonna iterate through the neighbors of the node. And so for every neighbor, let's say V in the adjacency list of the node. And so for every neighbor V, actually I'm going to make a separate variable. So our new cost to V, if we were to take it from this node, that would be dist at node plus 1. And so because it's a neighbor, it'll only cost us one more to get there, right? So dist at node plus 1 is going to be our new cost. And if this new cost is smaller than dist at V, the distance is better than the current distance to V, update V, and push into Q. So then dist at V is equal to new cost. Actually, I'll put this comment. Update dist at V. Oh, okay. And then Q dot push V. Push neighbor into Q. Okay, and let's see what that gets us. So we're going to iterate through the nodes and see if it calculated the distance correctly. Okay, so it's saying the distance from 1 to 1 is 0, which is correct. The distance from 1 to 2 is infinity, and that means that it cannot reach 2. And if we look back at our graph, 1, we can go to 3, we can go to 5, we can go to 6, but then we reach a dead end and we can't go to 2. And so that would be correct. Oh, wrong application. And so we indeed can't reach 2, and that's going to leave the cell to infinity. Well, not actually infinity, just the large integer that we're using to represent infinity. To node 3, it's saying it has a distance of 1, and indeed it does have a distance of 1. To node 4 and node 5, it's saying it has a distance of 2, and so from 1 to 4, that would be 2 edges. 1 to 5, that would be 2 edges. And this is 1, 2, 3, 4, 5, 6, 6 and 7. It's saying has a distance of 3 and 1, 2, 3, 1, 2, 3. And to 8, once we reach 6, there's only a directed edge from 8 to 6, but not from 6 to 8. So we know that it's going to be impossible to reach. So the distance is infinity. And so that's how you use breadth first search to calculate single source shortest path on the unweighted graph. Now, if this graph had edge weights, if this graph had edge weights, for example, if this edge had weight 8 and this edge had weight 6, etc., and if we had a couple more edges, then we can't do shortest path this way. We're going to talk about how we do that later. But for graphs that aren't weighted like this, then we can calculate distance with BFS. Are there any questions? Okay, if not, I'm going to move on to DFS. So DFS is actually much more commonly used than BFS. The idea of depth first search is that it goes down the path as far as possible, and then it goes on to explore other paths once it reaches all the dead ends from a single node. And so you should know these algorithms from junior stream, but if you forget, you can always ask questions if you don't understand anything. Okay, so the common applications of DFS, again, can test for reachability. It can detect cycles. You can find connected components. You can find bridges, and you can topological sort. And we're going to talk about topological sorting today as well. Okay, so let's go over an easier example at first. So this says some video game stuff. World of StarCraft features N planets numbered 1 to N. Each planet is under the control of one of the 3 races. And so it just has P, T, and Z for the 3 races. And there are M space routes running among the planets, with the ith space route allowing one to travel in either direction between planets AI and BI. There may be multiple space routes connecting a single pair of planets. Now, it's important when you read problem statements to read whether it's a directed graph or an undirected graph. In this case, if you can travel in either direction, that means it's going to be an undirected graph. Despite its secretive and unreleased development status, World of StarCraft somehow already has an enormous player base. He has K friends in the game, and his ith friend is on planet X and would like to reach a different planet Y to complete an objective. And when a player is on I, he may travel along a space route J when they're connected, and it's only safe to do so if both planets are under control of the same race. And he would like to help his friends to complete their objective and help them determine how many friends he has such that it's possible to safely travel through a sequence of planets. Okay, so for, this problem is about connected components. So first of all, we're only going to accept space routes if the 2 planets it connects is from the same race. That's the first condition of the problem. The second condition for X and Y to be connected is if they're in the same component. Now, since this is an undirected graph, all we have to do is to label each node with a specific color. So for every component, we're going to assign it a unique color. And if 2 planets have the same color, then that means that they're from the same component. Should I use this as an example? I think this could be large, but maybe not. I'll try it. Okay, so this is from P, Z, Z, P, P, P. So these are the races of the planets. And so 1, 2, there can't be an edge. 6, 4, there can be an edge. 3, 4, no. 2, 5, no. 5, 6, yes. Wait, I'm just seeing how many edges there are that are related. 1, 2, 3, 4, 5, 6, 7. Okay. 5, 6, yes. 1, 4, yes. And 4, 2, no. So the only real edges that count are 1, 4, 4, 6, and 5, 6. Let me put that onto the graph editor. Okay. And then it's asking for whether 6, 4, and 4 are connected, whether 2 and 3 are connected, and whether 1 and 5 are connected. And so 6 and 4, they are connected, so that would be valid. 2 and 3, we can go see that they are not connected. And 1 and 5, they are connected, or undirected, yeah. they are connected again. And so what I mean by connected component is if all the nodes if every node and an undirected graph like this is connected, then we call it a component. And so 1 can reach any other node in the graph, and 4 can reach any other node in the component, and so on. And 2 and 3 would not be in the same component because it can't reach the nodes inside of that component. Okay, so how would we solve this problem? Let's first take in the input. So if I have n, m, and k, so n, m, k, and then we have a string r. Okay, and the next m lines are going to be the edges. So looping I from 0 to m minus 1. Okay, so let's take an input of the starting node and ending node, and remember to only add it as an edge if they're from the same race. So if r at a minus 1 is equal to r at b minus 1, and remember to subtract 1 here because the planets are 1 index, but strings are just 0 index by default. So we need to subtract 1 to offset that. Then we do adjacency at a dot in place back b. And since this is an undirected graph, we also need to do the exact same thing to add a as a neighbor of b. Okay, and for the next k lines, it's going to ask us the queries. Now, before we answer these queries, like I said, we want to color each connected component a unique color. And so if 2 planets are of the same color, you know they're of the same connected component, and therefore they can reach each other. And so that's the main idea behind it. Now, you can obviously traverse the entire connected component with BFS or DFS, but DFS is usually preferred because it's very simple to implement. Let's make a global variable. Actually, I'll declare all my other variables first. So let's make an integer array color. How many nodes do I have? Okay, and oh no, just 10 to the power 5. Okay, let's declare a function dfs, and that's going to take in a node u, and let's declare a global variable int, let's say col for color. Okay, now for every single node in the graph, if it's not already colored, so if color is equal to 0, then we're going to perform DFS on the node of the graph. So DFS at I. But before we do that, we're going to increment color, or the current color here. So if we increment this color, then every single time we do this DFS, we're going to have a different COL value. And if we have the same COL value for 2 nodes, then we know that it was both the nodes were reached in a single DFS. And what that means is they're in the same connected component and they can reach each other. Okay, so let's, when we reach node u, we're going to say color at tu is equal to COL. And for every neighbor of u, v, So for v and ADJ, I'll declare that as well. So for every v that is a neighbor, for every v that is a neighbor, if the color of v is equal to 0, or if it's equal to 0, or if it's, if it's equal to 0, then we say the node is uncolored, and so we perform DFS on that node. And let me take an input here. And in the end, after we have, it's already here. Okay. And in the end, after we perform all the DFSs, we can answer the K queries. So integers x and y, we want to see if x and y are in the same component, and they wanted us to find the number of pairs x and y that are in the same component. So answer plus equals color at x is equal to color of y. And finally, we print the answer. Okay. Wait, no. 2, yeah, it should be 2. I think, did I miss anything? I'll submit this. Okay, that should be correct. So I'll just go over what we did again. So for every edge, we first checked if the two nodes are of the same race, because the problem said that you can only safely travel between two nodes if they're of the same race, under control of the same race. And once we found a pair that satisfied that, we first added B to be a neighbor of A, and then added A to be a neighbor of B, because this is an undirected graph. And then afterwards, for every single node in the graph, we wanted to perform a depth-first search just to traverse the entire connected component that is reachable from this node. And we're going to color it. We're going to color each iteration a unique color, so we know which two nodes are of the same connected component. And so we add on, we increment color whenever we reach a node that is equal to, whenever we reach a node that is uncolored, and then we perform depth-first search. And afterwards, when we have two planets x and y, and we want to know if if x can reach y, then we just see if they're in the same connected component by checking if they have the same color. And finally, we output the answer. Are there any questions? If you're wondering why I don't implement DFS with stack, it's because recursive DFS is just much easier to implement, as well as it can do more stuff. So later you'll see, or maybe next week, you'll see that we can put stuff at the end of DFS as well, because it comes back to the original node after going through all the nodes that are reachable from the current node. And so that's sometimes a very useful property of recursive DFS. Okay, so moving on to did I say everything I wanted to? They have the same complexity, and they can do some of the same things, like finding reachability but they're different in nature. BFS is used mainly for a single source shortest path on unweighted graphs, and DFS is more common because it's shorter to implement and it's versatile. Yeah, so DFS and BFS are both linear algorithms, and because they traverse each node exactly once, and they don't go back to the same nodes, and also they go through each of the edges exactly once if it's directed and twice if it's undirected. And you might say that in each call of the DFS, in which there are n calls, you're looping through the edges, which can go upwards to m. But over all of the calls of DFS, you're going to find that the sum of all these for loop calls is going to sum up to O of m. And so that's why, and m is referring to the edges, and n is referring to the nodes. So that's why DFS and BFS are both linear. Okay. Next, let's move on to, oh no, I wanted to talk about one more DFS problem. So, yeah, so this problem says there are a list of events, and there are some things you have to do before others. So for example, it says, do your math homework before watching television, do your math homework before you call your friend, etc. And so it just says event 1 has to be done before event 7, event 1 has to be done before event 4, event 3 has to be done before event 4, and so on. And so how we model this problem as a graph problem is each of the events is a node, and each of the constraints here is a directed edge. So for each of, let me draw the nodes 1 to 7, 1 to 4, 2 to 1, 3 to 4, 3 to 5. Okay. So these are the constraints on the events. And so you can see that 2 points to 1, and 1 points to 7 and 4, 3 points to 4 and 5. And they're saying they will add additional constraints in pairs, but not more than 10. So once we turn this into a graph, what we can do is called a topological sort. And so in a topological sort, the number that appears before so the number that appears afterwards can't reach the number that appears before it. And so you can almost think of it as like a flow chart. So 2 to 1 to 7. 7 won't ever appear before 1 or before 2. And 4 won't appear before 1 or 2 either. And 1 won't appear before 2. And so topological sort is going to help us solve this problem. Now the constraints on this problem are very small, and so there are other ways to do it. But just for the purposes of learning topological sort, I'm going to use that to solve the problem. Okay, so it's going to give us pairs of constraints and ending at 0, 0, so that's fine. I'm going to say while true, and if a is equal to 0, then we break. Otherwise, we're going to say adjacent to a is b, and it has these original constraints. So adjacent to 1 is 7. Adjacent to 1 is also 4, and 1 comes after 2, so like that. 4 comes after 3, and 5 comes up after 3. Okay, and so how we implement topological sort here is we use a stack. So first, let's just initialize a stack here. And in our DFS call, we're going to repeatedly add numbers into the stack. And the main idea behind topological sort, let me just type out the DFS function. So for every neighbor in the adjacency list at U, if it's not visited, then we're going to say DFS V. And the main idea behind DFS is that it's going to traverse to all of the nodes first, and then after it comes back to that node, so after reaching all of the nodes it can reach, add it to the stack. So s dot push U. And so outside of the in the main function, we're going to loop through all the nodes again. So and to perform DFS on every single one of the nodes. And I should remember that it goes up to 7 and not another number. Now there's an interesting property in this problem that says if there's a set of tasks which may be performed at the same time during the process, the smallest number of tasks should be performed first. And so due to this property, we're actually going to loop from 7 back to 1 because of how a stack works. And how a stack works is that if you push it in later, it's going to come out first. So it's known as last in, first out. And so if we loop backwards here like this, I is greater than or equal to 1. If we loop backwards like this, 1 is going to be traversed later, and that's going to mean that 1 is going to be pushed into the stack later, well, possibly later, unless a node before can reach 1, then it would be pushed in earlier. But otherwise, 1 would be pushed in later, which means it's popped out first, and that's exactly what we want. And so if the node is not visited, then we're going to perform a DFS on that. And finally, we'll say if, I forgot to deal with one condition here. There's a possibility that your events form a cycle. So for example, in the second input here, it has 2 going to 1, and then 1 going to 7, and then 7 going to 2. And so this cycle is going to make the topological sort impossible. And so this is something that we must take care of. And if there is a cycle that wants us to output cannot complete these tasks, go to bed. And so instead of returning void, let's make our DFS return a Boolean. And so it's going to return true if it finds a cycle. And actually, we're going to use the exact same idea as before to color the visited array with using a different color in each iteration. And so let's use, COL is fine. So let's increment COL, and if it's not colored, then we traverse. Yeah. Okay, and so in each iteration, it's gonna color a different color. And we're gonna set the visited at U to that color. And if V is the same, if viz at V is already equal to viz at U, that means in the same iteration, we visited V already. There is a cycle. Then we're going to return true. And if it's not colored, this should be viz. If it's not colored, then we're going to first of all perform a DFS on the node. And if the node returns true, then we also want to return true. Otherwise, if nothing returns true here, we're going to push the U into the stack, and we're going to return false. Okay. And here, if our DFS ever returns true, that means a cycle is found. And what we're going to do here is just output what they tell us to output here. And return 0. Just so we don't, we're breaking out of this for loop and also not running anything afterwards. And afterwards, if no cycle is found, then while the queue is, or not the queue, the stack, while not stack dot empty, we're gonna print out, do they want it in separate lines or a single line? In a single line, okay. So s.top space and then output a new line. Okay, I need to declare some variables here. So int viz at 10 vector int adjacency at 10. I don't know if I missed anything. Whoa, what happened here? Oh, I didn't pop the... So after you print out the top, you obviously should pop the whatever was in there into the array again. And what did I do here? Hold on. If it's not visited, increment the color. Cycle is found. Okay. Let me output the nodes I'm going to, just to see if I can find the error that way. Okay. So it's somehow never going to any of the neighbors. Why is this? Oh, I made a typo here. It should be viz at v. Oh, that's not what I meant. Okay, and let me remove my debug output here. Okay, and that should be correct. 3562147, and let's just draw the graph again just to make sure we're correct. So 1 goes to 7, 1 goes to 4, 2 goes to 1, 3 goes to 4, 3 goes to 5. And the additional constraints here, 6 goes to 2, and 5 goes to 4. Okay, so the answer is 3, 5, 6, 2, 1, 4, 7. And we have 3, 5, 6, 2, 1, 4, 7. And let's see why this is fine. So if we have 3, 5, then that would work, but we can't put 4 yet. Otherwise, these things that come after will be able to reach that node. And so after we put 3 and 5, we should put 6, 2, 1, and then all the way to 4 and all the way to 7. And they're breaking ties by doing the smallest number tasks first. And that's exactly what we're doing as well. And so let's try this code. Okay, so that worked. So remember, the key part about topological sorting is you go through the neighbors of U first, and after you reach all the nodes that it can reach, you push it onto the stack. And in the end, you just pop everything out. Okay, that should be it for topological sort. It's been an hour already, somehow. Okay. Let's move on to Dijkstra's quickly, and I also want to go through Kraskel's algorithm today, hopefully. So Dijkstra's algorithm with priority queue is used to find the lengths of the shortest path from one vertex to all other vertices in a graph with non-negative weights. And usually the graph theory problems you meet will have non-negative weights because it usually doesn't make too much sense for an edge or a distance to be negative. And so that's why Dijkstra's is so popular. And it has a very good complexity, and it solves the popular cases for graph theory problems in competitive programming. And so the complexity of Dijkstra's is O of E log V, where E is the number of edges and V is the number of nodes. And so let's review the implementation of Dijkstra's. And so this says just solve the single source shortest path problem. Okay, so we have n, the number of vertices, and m, the number of edges. And for the next m lines, we're going to take in integers a, b, and c. And for Dijkstra's algorithm, you obviously now have weights on your edges, so you're going to need to add your weight of the edge into the adjacency as well. And so instead of just having vector int, we're going to have vector pair int. 1000. Int max n is equal to 1005. Okay, so always check that it's bidirectional edges. That means it goes both ways, so it's undirected. So we're going to need to add b as a neighbor of a, so we're going to place back bc, and also add a as a neighbor of b, and so that's in place back a, c. Okay, and that should be in it for taking the input. And for setting up Dijkstra's, it's the exact same as what you would do as for a single source shortest path on a BFS. Just for the setup part, not the algorithm. So first let's have a distance array. So we have dist at max n, and we're gonna fill the array with very large integers. So dist 0x3f, size of dist. Okay, and so we know the distance from 1 to 1 is 0. And we know that to implement Dijkstra's, we need a priority queue. And if you don't know what I'm talking about, I think the juniors learned Dijkstra, so you can go check out that document that Gordon had with Dijkstra's. But I think most of you should know what Dijkstra's algorithm is. So for priority queue in C++, obviously we store a pair of integers, the cost and the node. Make sure you always put the cost first so it sorts correctly. And so you put the data type here, and then you put vector pair int int, and then you put greater pair int int. And so the reason you have to put greater pair int in is because in C++, priority queue takes the maximum value by default. And so if you don't put this, it's going to give you the most expensive path so far instead of the least expensive one. So you have to put this argument. Okay, and while the priority queue is not empty, so while not pq.empty, let's declare variables cost and node. And let's use the tie function. I don't know if I've explained it before, but if you put tie and just the number of variables here, you can set that equal to pq.top, and then we pop that from the priority queue. So what this does is it assigns cost to the first of the pair and node to the second of the pair. And an important step here is that you make sure that the distance at this node is actually equal to the cost. If it's not equal to the cost, then we don't want to be processing this because this pair is actually expired. Okay, so now we loop through the neighbors of the current node. So we know that each element in the adjacency list is actually going to have 2 integers, so this is going to be a pair of integer. So let's put t for temporary. So for auto t in adjacent of node. Okay, if let's define an integer new cost. So we know that t.second is the cost of the edge, and the current cost of from 1 to this node is going to be stored in cost. And so the new cost going from 1 to t.first is going to be t.second plus cost. And if this new cost is better than the distance from 1 to the t.first, then we're going to update t.first, dist at t.first. And so, and then we push it into the priority queue again. And make sure you have the order correct. So first you want to push in the new cost. So the cost first, and then the actual node. So t.first. And if you're wondering why the first one is the node, that's just how we pushed it in the beginning, like that. Okay, and in the end, it wants us to output each of the ones in separate lines. Okay, each of the distances. So looping through all the nodes, we're going to output the distance from 1 to that node. Now, if the distance from 1 to that node is equal to the very large integer that we put in before, and that'll be stored in dist at 0 because we'll never go there, then we're going to output -1. Otherwise, we're going to output distance at I. Oh, I didn't and declare my variables. Okay. Huh? Oh. What did I do here? Oh. So you need to actually push 0, 1 into the priority queue. And so I should clarify that this is a pair of cost and node. And so from 1 to 1, our current path cost is 0 because it's the exact same node, and the node that we're on is 1. Okay. All right. Let's put that in. Okay, so that worked. Are there any questions about Dijkstra's algorithm? Or rather, how to implement it in C++? I think all of these implementations are going to, I'll upload them onto GitHub later tonight, and yeah, if you want to go back to it, it'll be on GitHub. But if there are no questions, then I'll move on to something that you guys might not have known before. So we're going to talk about Kraskel's algorithm. And so this is the most common algorithm to find the minimum spanning tree of a graph. And so first of all, what is a minimum spanning tree? Let's just have a graph. Let's say we have what? Oh, well, actually, I needed to create a weighted graph anyways, so that's fine. If we have a graph just with, let's say, 4 nodes, just to keep it simple, and this has weight of 3, this has a weight of 4, this has a weight of 1, and this has a weight of 7. The minimum spanning tree is a tree that whose nodes are the nodes in the graph. So a minimum spanning tree has to cover all of the nodes in the graph. It has to reach all the nodes, and it has to have exactly n-1 edges. Otherwise, it wouldn't be minimal anyways. So for this graph, the minimum spanning tree would use this edge, and this edge. And the sum of these edges has to be the minimum. And so 1 plus 4 plus 3, that's going to be the cost of the minimum spanning tree of the graph. We don't include the 7 because it's the most expensive. And we could have also added edges here. And if it was cheaper, like, actually, I'll just make a new graph for that. If we had 1, 2, 3, 4, and we had 2, 3, 1, 7, 6, then instead of taking this edge that's 7, we would take this edge that goes from 1 to 4, but we still need to reach this 3 because it has to reach all the nodes. And so this is a 2. And then we can take this edge to go from the 4 to the 3. And then between this 1 and the 6, we can choose the one with the 1, and our minimum spanning tree would use these 3 edges. And it would have cost 1 plus 2 plus 3. And so we can use the edges to use the other edges to avoid using the expensive edges. And the idea of Kraskel's algorithm is that we're going to sort all of the edges. We're going to sort all the edges in non-decreasing weight. And for each edge, if the 2 nodes it connects aren't already connected, then we're connecting the 2 nodes with merge AB, and we're adding the cost to the total. Now, how can we know that 2 nodes are already connected in a graph? And that's where we're going to use a new data structure, and it's called union disjoint sets. And so we're going to learn about the technique of union find. Let's first, at first, every single node, the representative of every single node is itself. And so if I try to merge 2 nodes, then it looks for the representative of the first node, and that's going to be itself, because at first it's going to be just the set of 7 that 7 is in. The head of this set is going to be 7. And for the other node, it's also going to search for the representative. And it's going to link the 7 to the 5. And that's how it's going to merge the two nodes. And as we do more and more of these, say we wanted to merge this 6 and this 5. First is going to find the representative of 5 and by moving towards the root. And so it knows that the representative of this set is 7, and it's going to merge these two nodes because 6 is the representative of the set containing 6, and it's going to link them together again. And we can just keep going. Here we're linking the 7 and the 3, and it's going to link the 3 to the 7 as well. And it's going to link more and more nodes. And if I just make it randomly union like that, I think now we can start visualizing the finds. So how you would find a node in the graph is you would just keep moving towards the root. And that's the whole idea behind disjoint sets. And for sets that only have one element, obviously it's the root itself. And so how we're going to implement disjoint sets is we're going to have an array parent that's going to store the representative of this, or rather the node that is above the current node. And so for example, parent at 0 is going to be 1, parent at 9 is going to be 1, and parent of 1 is going to be 7, and parent of 7 is going to be 5. And so each time we're at 0, we just call parent of 0, and that's going to bring us to 1, and parent of 1, which is going to bring us to 7, and then parent of 7, which is going to bring us to 5, and that's how we're going to move towards the root. Okay, let's just go to this problem so we can implement Kraskel's algorithm. And so this problem says minimum spanning tree of graph is defined as a tree which contains all the vertices and does so using the smallest accumulative weight of edges. You are given a graph in a shape of line. It has n vertices and n-1 edges, where the ith edge connects vertices I and I plus 1 using weight wi. You are also given an integer k. There exists an arbitrary number of network trampolines indicating that a weightless edge connects the ith vertex to the I plus kth vertex. Given that both exist for all values of I, you are also allowed to use the other existing edges as necessary. All edges are undirected. Find the minimum spanning tree of the graph by outputting the sum of the weights of all encompassed edges. So the part about the ith edge connecting to the I plus 1 edge and the ith connecting to the I plus kth vertex is not important for Kraskel's algorithm. Kraskel's algorithm is going to work for any graph as long as a minimum spanning tree is possible to be constructed, but I'm just using this problem as an example. So first of all, we're just going to get all of the edges from the input, and then you'll see how we implement Kraskel's. So we have n and k. And it says it's going to have n-1 integers representing the weight from I to I plus 1. So I equals 1, I is smaller than n, and we're going to declare a variable that stores the weight, and we're going to push in an edge that contains the weight as well as the two nodes it's connected to. And so for this, let's define a vector of edges. And so we need to store three things: the cost and the two nodes, right? And since we want to sort by the cost, we're going to put it as the first parameter of the pair. So that's going to be an integer. And for the two nodes, we can put that inside of a pair. And so we're going to have a pair inside the second element of the first pair. And afterwards, we're going to store all that into a vector. Okay, so let's name this vector edges. So if, not if, edges dot push back. So the weight first, and then we have a pair of from I to I plus 1. Now, the way you take an input is going to depend on the problem. It's just this problem had a unique constraint on the edges, I guess. And if I plus k is smaller than or equal to n, it says it's going to have a 0 weight edge from I to I plus k. Okay, and that's it for the input. Now, let's going back to our Kraskel's algorithm. First, we're going to sort all the edges in non-decreasing weight. And so sort edges dot begin, edges dot end. And for each edge, if the two nodes it connects aren't already connected, then connect the two nodes, etc. So let's iterate over each edge. So auto e and edges. So let's name the three variables as a, b, c. So c is equal to e dot first because that's the cost. I'm letting c be the cost. And again, we can use the tie function to assign a, b to be the two nodes of that it connects. Okay, and if a and b are not connected yet, and so later we're going to make a merge function that'll return true if they're not connected and merge them, then we'll add the cost to the total. So let's make a variable answer, and answer plus equals c. Okay, and now let's talk about how we actually implement the disjoint sets. So as actually I'll declare the other variables first, and it goes up to okay, as I said, we're going to have an array called parent at max n, and that's going to make room for every single node. And at first, the parent of each node is itself, and that means that it's the representative of the set. Parent at node at I stores the node above it in the set. If the set has size 1, the node will have parent that is itself. Okay, let's first define a find function. And so remember what we did here. If we use find on, let's say, okay. If I use find on 9, then does it work this way? I hope so. Okay. It stopped working for some reason, but it's fine. So if I try to find the representative of the node 9, then all I do is I call parent of 9 and I get 1. I then call parent of 1 and I get 7. I then call parent of 7 and I get 5. And so this is a recursive process, and we can solve this find function with recursion. So let's put int find to have taken variable node. We know that if the set has size 1, or I should say if the node is the representative of the set, then the node will have the parent that is itself. So if node is equal to parent at node, then that means this node is the representative. Then return node. Otherwise, I'll put else just so it's clear what I'm trying to do. Otherwise, I'm going to return find parent at node. So we're going to find the parent of the parent of node, or find the representative of parent of node. And now for our merge function. First of all, we need to find the representative of any two nodes. So actually, if I clear this, I hope it works. Well, okay, yeah, so it first needs to start searching for the representative of the two nodes. And then it's going to link the two nodes. So let's define A, or PA is equal to the representative of A. So PA is equal to find A. And PB, we're going to define that to be find B. If they already have the same representative, so that means if they already are in the same set, then they're already connected. So if PA is equal to PB, then we're going to return false. And so that this if statement won't run. Otherwise, what we're going to do is attach the parent of PA to be PB. Or you could also do it the other way around. That should work as well. And in the end, we're going to return true. Okay. Let's see if okay, so we first need to initialize this parent array. So before we do anything, we're going to make a for loop from 1 to n. And the parent of I is equal to I. And that'll make I the representative of its set. And that should make our algorithm work. 5, 3, 11. Okay, I don't know if this is going to TLE because I still have more optimization to do, but I'll just try to see if this is at least correct for now. It should. Time limit, yeah, okay. So based off of this idea, we're going to apply two optimizations. So first of all, instead of having a very long path like this, we're going to have to go 2 to 5 to 8 to 7. That's going to be linear in terms of the height of the tree, right? And instead of doing that, what we want to do is, after we know that 7 is the head of this entire chain, we just put 5 directly at the root of 7. So next time it'll just take one single iteration or a recursive call to get to 7. And the way we do that is we just say parent at node is equal to find parent at node. And so redefine parent of node to be the representative. And the second optimization we can do is we're going to attach the smaller tree to the bigger tree. And that's going to help us get a tree that is not as deep as well. And so let's keep an array size at max n. So Now that we have a set size, each of the set is going to start out with size 1. So size at I is equal to 1. And from here, when we merge the two sets, first we check if size at A is greater than size at B. If so, let's just swap A and B. So the purpose of this is so that make sure A is or PA is the smaller set. And what we do now is after we say parent at PA, this should be PA, and this should be PB. After we let the parent of PA be PB, then we're going to add the size of PA to PB. So PB plus equals size at PA. And so the size will be updated that way. And so these two optimizations should be able to allow us to pass. Okay, and yeah. And so that's Kraskel's algorithm. Are there any questions? Okay, all of this code will be posted on GitHub later tonight, and if you want to refer to it, it'll be on GitHub. And yeah, I think that'll be it for this lesson. Thank you for coming, and we'll see you next week.